Thank you, Hans. Thanks for the introduction. And again, apologies for the technological issues there. Hi everyone. It's great to be here today and to speak to you. And this is actually the fifth webinar that Richard and I give in less than a month on this report that we've published in March. And as all of you, I'm talking to you from our home today. So apologies in advance for any background noise you might be getting. My children, very young, are downstairs and play, and they can be pretty noisy sometimes. I hope they behave. And we will now speak to you about the principles and policies for heat electrification in Europe more generally. So we don't really speak about a specific country, but we just draw some general conclusions for European countries more generally. And this presentation is largely based on the report which we published in March. And it's a very big topic, and we appreciate there's been a lot of work already done, and we try to distill that work into some overarching principles and policy recommendations. So before we start, Richard and I should also disclose that we're not just analysts of policy, but also consumers who've actually experienced heat decarbonization in our own homes. So this is my house in Oxford, from which I'm talking to you today. And we have upgraded the energy efficiency performance of the house significantly over the years, and also installed an air source heat pump last year, about a year ago, pretty much exactly. And I've sort of run some initial calculations, and I measured that we probably reduced carbon emissions by about 60% through doing the energy efficiency upgrade in the air source heat pump. And we also enlarged our house, so per square meter consumption has reduced by actually almost 3/4. And Richard, who is based in Falmouth in Cornwall, has done something very similar. He has also refurbished his home extensively and has put in a clean heating system. And he will talk about that later on when he starts his part of the presentation. Let us now begin with the main part of our presentation. It's structured in the following way. So first, Richard Lowes will present the wider context around heating and heat decarbonization. He will then talk about specifically why we believe electrification coupled with energy efficiency is a key option for heat decarbonization, not the only one, but one that we think is very important. And then I take over and present on the 4 principles that we've developed for heat electrification before I talk about the policy logic that we believe will be needed to deliver on the 4 principles. That's a structure that we follow. And Richard, I will keep skipping through the slides just to make things a little easier and avoid any technological glitches here. Richard, over to you. I hope people can hear you. I'm going to mute myself now for the next few minutes until I take over again.
Thanks very much, Jan, and good afternoon, everyone. I hope you can all hear me okay, and a huge thank you for joining us this afternoon. It looks like we have attendees from across the world, which is wonderful, and also some names that I recognise from closer to home, so that's great too. So the first thing I really want to say is that in doing what I did to my house, which is actually a fairly average house in UK terms, fairly small, it's a mid-terrace, I've actually reduced the carbon emissions from the heating by around 85%. And that was extensive energy efficiency measures, including an air source heat pump, which replaced the gas heating. So what this says is that rapid progress is possible now, and it can be done in existing houses. It doesn't necessarily say that that's easy, but progress is possible. So a bit about me. Well, I've been working on heat decarbonisation for over a decade now, initially working in the gas industry for a UK gas network operator, and for the last 6 years I've been in academia. And actually in the past 10 years, not much has changed for heating in Europe and indeed in many other global countries. And that's despite the fact that we knew about climate change many years ago. So the challenge we have now actually hasn't really changed in 10 years, but what has happened is that the Paris Agreement has come into force, and with various targets for net zero and zero carbon targets, the heat system still needs to be transformed, but it actually needs to be transformed even more rapidly and even more deeply than we previously thought. Okay. Next slide, please, Jan. Thank you. So there has been a great deal of focus on the electricity system and the decarbonisation of it over the past decade. It's obvious that great progress has been made. We've seen amazing cost falls in the cost of wind power and solar power in particular, in terms of storage costs as well. And all of these things are extremely positive for various reasons, including how they connect to heat decarbonisation. And I'll come back to this. And the deployment of renewables really is happening more quickly than many expected, not everywhere, but in certain countries. However, as this pie chart shows, and this is for the EU, it's not all about electricity. In fact, half of the heating that is used across the EU is actually for heating and cooling, the vast majority actually being for heating. And if we look at that in a bit more detail, the sub-pie chart on the right shows that the biggest part of that is space heating, and that is primarily keeping people warm in their homes and in their workplaces. And just looking at the existing heat generation mix in the EU here, what we can see is that presently 75% of heat in the EU is generated from fossil fuels. The biggest chunk of this is gas, but it varies geographically. It also includes coal and oil in different countries, and between countries it varies quite significantly. But really what this shows, and the point that we're trying to make here, is that without tackling heat, you can't do decarbonisation. The simple goal really is that if zero carbon goals are to be met, no fossil fuels can be burnt for heating. I mean, that's quite obvious, but it does represent a transformational change to the sector. Now, it's also worth pointing out before we move on that not all heat is the same. This isn't necessarily obvious, but heat use in the industrial sector has some very specific qualities, particularly around the temperature of heat required, something that's often referred to as the grade of heat. Some processes simply can't happen without very high temperatures. For example, glass can't be manufactured or melted without high temperatures. Now, those high temperatures aren't necessarily needed to heat homes. And in fact, most heat is used to generate much lower final temperatures. For space heating, for example, at 20 degrees, and the production of hot water maybe at 50 or 55 degrees, but actually an even colder end-use temperature. Overall, the largest segment of heat use in the EU is for space heating in people's homes. And this is where our report is focused. And I should say we also consider hot water because the two are very closely aligned in terms of their systems. The other thing I'd say is that if you look at the tertiary sector on that graph, that includes things like hospitals, businesses, schools, the big heat demand in those sectors is also space heating. So that means that many of the principles that we propose that are primarily focused at the domestic sector can also be applied to the service sector as well. Now, I said that not much had changed in the past 10 years, and that is roughly true to a point. A recent paper that was published only this month shows how the carbon emissions from heating have changed in the EU since 1990. And actually what we do see is a fall in emissions from 1990. And the graph on the left shows total emissions from residential heating by different fuel use, and that's coal in purple, oil in the top in that turquoisey green, and you can't quite see on the presentation, but the middle section, that blue, is natural gas. Now, what this graph shows is a combination of two things, or it shows the results from a combination of two things, I should say. What we're seeing is a reduction in overall emissions, and that's part in due to energy efficiency, but it is also in part due to some fuel switching from oil and coal to gas. And you can actually see that in this graph, the emissions from the gas sector have increased between 1990 and 2015, and from the other two sectors, they have reduced. And at the same time, energy efficiency is playing its part. So we've seen some change, but primarily this change links to changing uses of fossil fuels and some energy efficiency reductions. And the graph on the right-hand side breaks this down in a little more detail by country. Overall, you can see significant change in some countries and little change in others. But this change, quite simply, isn't fast enough, and it really is the growth of low carbon heating that needs to be the focus. Thank you. So I'm actually now going to talk about the options for low carbon space heating and why currently electricity as an option appears to be so important. So it's often said that there are many, many different ways to decarbonise heating. And it's true to say there are many things you can do to actually decarbonise heat. But actually, there are only a few technologies which can deliver low carbon heat. So there are only a few ways really of generating low carbon heating in the first place. And for some of these, it's difficult to see how they can deliver at scale. So solar thermal is a very low carbon technology. It can be a relatively cost effective technology. But the issue for countries at higher latitudes, in countries where there's a significant heating system, for example, the UK, France, Scandinavia, North America, solar thermal can't provide reliable output on a cold and cloudy day. In fact, heating systems will generally be designed as if the solar thermal isn't present because the solar can't be relied on. What that means in practice is that if you, for example, have a heat pump system, that heat pump would be designed to match the maximum demand of the house, ignoring the solar thermal if it was there. And that's simply because on the coldest day of the year, you can't rely on that solar thermal to produce any power. Now, this isn't saying that solar thermal has no role to play. And we are seeing some actually quite significant growth in certain Northern European markets. Denmark in particular has a significant capacity of solar thermal, but this is often linked to interseasonal storage sites, so big thermal stores, and also connected to district heating networks. Obviously, there are space and availability constraints around this. So bioenergy is also a potential low carbon heating option, and this could include biogas or biomass combustion, but it's naturally limited by its availability. There are also, of course, concerns over local air pollution and questions over wider sustainability issues. Another option is potentially deep geothermal. That is where deep heat is extracted from below the Earth's surface. And this could have some role too, but its potential is limited by requiring heat resource to be near to the heat demand. And this may often also require a heat network as a distribution system. And I should just make it clear, we're not talking about ground source heat pumps, but we're talking about deep geothermal where deep drilling is required. And finally, another option for heating, for low carbon heating, is potentially hydrogen, which is being promoted by some, and I say some, primarily those people that are in the gas industry. And hydrogen really is a deeply uncertain technology, and it's unlikely to deliver anything within at least the next decade. It's still very much at the experimental stage. So electrification is a potential option that actually can fill that gap immediately. So the expected widespread use of electricity for low carbon heating has been known for over a decade. Various countries have attempted to support some degree of heat electrification. Now, electrification is quite simply important because we know how to produce low carbon electricity, and it's quite easy to turn electricity into heat. Heat pumps are an important technology because they generate more useful heat than the energy that you put in from the electricity. It's also worth saying heat pumps can also be connected to heat networks, so they are quite a versatile technology. Now, electrifying heat shouldn't be seen as easy. Lots of practical on-the-ground action is required across Europe and indeed the world. However, the reductions in the cost of renewable electricity I mentioned have been staggering. These reductions can feed through to electrified heat. The UK's statutory advisor, the Committee on Climate Change, has suggested actually that because of the cost reductions, reaching net zero will actually cost what they thought the 80% reduction, the previous target the UK had, would cost. Those cost reductions effectively mean that extra 20% emission cut is free. So just looking at this graph then, it may look complex, but don't worry, it's really not. It just shows the emissions intensity for electricity in various European countries. The central line there, which is the flattest sort of pinky purple line, that shows the average EU emissions electricity intensity from 1990 to 2016. And what you can see is a significant and steady decline in the carbon intensity of European electricity on average. That's in part due to the growth of renewables and also due to the reduction in the use of coal in many countries. And as those renewable costs have reduced and continue to reduce, we expect those emission intensities to reduce further. There is obviously variation between different countries, but the direction of travel in many countries is clear. Okay. So this graph actually shows in detail the UK picture, and it's produced by an academic in London, but for the Drax electricity generation group. And it shows how reducing electricity emissions intensities feed through to electric heating technologies and compared to gas. What you can see there, gas is represented by that purple line in the middle, and that's been roughly flat. And that's gas for heating, I should say. And the falling electricity emissions intensity in the UK is shown by that blue line, which says basic electric heating. Now, even basic electric heating, that's using resistive heating, so simple panel radiators or immersion heaters in water tanks, even that now has a similar emissions intensity compared to gas. However, if you use that electricity in heat pumps, because of the effective conversion factor of heat pumps, what's often referred to as the coefficient of performance, you can divide the emissions intensity of the electricity by that coefficient of performance. And you can see the examples on that graph there show for a coefficient of performance of 2, that effectively halves the emissions of intensity of the electricity, 3 is 2/3 off, and 4 so on. Now, my heat pump has a rated coefficient performance of 3.58, meaning that currently it's actually 3 or 4 times lower carbon than gas. Obviously, as the UK builds more renewable electricity capacity, which the country is planning on doing, particularly offshore wind, these emissions intensities will fall further. So basically, my house is future-proofed. So clearly the potential is there to make rapid emission reductions immediately using known technologies. And I just want to say something about my research before I hand over back to Jan. So my own research has shown actually in the UK recently that policymakers view heat decarbonisation as fundamentally disruptive, uncertain, and with little upside for consumers. It's not viewed particularly positively. I don't think that needs to be the case. And if heat decarbonisation can be done in a smart, coordinated, and integrated approach, there can be significant system and consumer benefits in terms of both carbon, comfort, costs, and the overall transition. So I won't say any more, but I'll now hand back to Jan, who's going to be talking about how we can best support these changes.
Thank you, Richard. So Richard outlined how important electrification could be for decarbonising heat in the next 5 to 10 years, and possibly beyond that. And in order to maximize the emission reductions from this process, we have developed 4 principles for smart electrification of heat. And I'm going to walk you through each of those principles now. And the first principle, and that's what you would expect from someone who has worked on energy efficiency for more than 15 years, is to put efficiency first. And we haven't really talked about energy efficiency so far in this presentation, but it should always be the first step that's undertaken to decarbonize heating. And the main reason for that is that it reduces the system cost of doing that. All the major studies that have been done by institutions like the IEA at international level, the modeling by the European Commission at EU level, at the latest time for the Clean Energy for All package, for example, analysis at national level by several governments, all these studies have shown that energy efficiency is needed to make a major contribution to heat decarbonization and would significantly reduce the cost of doing that. So that's one really important reason. And the second and often overlooked reason why efficiency is so important is that energy efficiency provides thermal storage capabilities for the buildings that get upgraded. In other words, you turn buildings that are highly efficient into what you could call a thermal battery that allows you to store heat for much longer periods of time than in inefficient buildings, which in turn then these buildings can act as a flexible resource to balance the power system when the heating is electrified. Now we'll talk a little bit more about that when I get to the second principle. And I want to show you some data from Tado, a German smart thermostat manufacturer. They produced this report this year in February. It got a lot of attention, and they essentially measured the heat loss in over, I think it was 80,000 homes they had data for, in several countries in Europe. It doesn't cover all of the EU member states, but quite a few. And what the Tado study has shown is how long a building can store heat and what the temperature loss is when it's 0 degrees centigrade outside, and inside you have 20. And after 5 hours, what the change in temperature is. And that's what this slide is showing. And you can see that in the most efficient buildings, specifically in the Scandinavian countries, actually the temperature loss is relatively minor. It's only about 1 degree centigrade. And that's for a 5-hour period. So the top runners, according to Tado certainly, are Norway, Sweden, Denmark, Germany and Austria. The place that does worst is the UK, where I live, and that's mainly the result of a very old and very inefficient building stock. But this data shows that even in very cold countries, in Sweden and Norway, you can store heat for quite long periods of time without a significant loss in comfort. So why is this ability to store heat so important? And this gets us to the second principle. So the second principle is to recognize the value of flexible heat load. One reason for operating electric heating systems flexibly is to avoid peak hours when it's particularly costly and often also very carbon intensive to generate electricity, and also to avoid unnecessary network upgrades. This is often an issue that people discuss when heat electrification is being analyzed, and without any flexibility, there could be significant costs for network upgrades that could be avoided. And a recent study by Everos Partners that came out 3 weeks ago actually looked at how much peak shaving could we do by combining smart and flexible heating with electric vehicles and the smart charging of those. And they suggested up to 40% of peak load could be avoided by doing that in homes that have a smart system for managing this. So that's one important reason. And another reason for doing it is that renewable electricity generation may actually not coincide with heat demand if it's unmanaged. So a good example of that is wind generation, for example, which may occur during the night. And preheating buildings overnight can take advantage of that. Preheating and cooling is a really good strategy because buildings are actually pretty good at storing heat at a much lower cost than storing electricity in batteries. There's also some experience with heat batteries to complement thermal storage capabilities of buildings, but so far that market is relatively small and relatively immature. And I think in the next 5 years, we probably see some real advancements with heat batteries, which could even enlarge the flexibility potentials in buildings even further. And I need to mention district heating here. District heating works extremely well with large-scale heat pumps. And the really big advantage of district heating over individual heating systems is that it offers the ability to store heat for several weeks and even months when connected to heat storage devices. And those include, for example, very large storage tanks, could be very large water tanks, pits, groundwater carrying layers. And in Europe, large-scale seasonal thermal energy storage has actually operated for many decades, since the 1970s with the first pilot projects in Sweden. So it's not something that has never been done and tested. We know how to do it, and the technology already exists. And district heating offers some real advantages there over individual heating because of that huge potential to store heat for much longer periods of time. And I want to give you one example of the value of flexibility that's from a very recent study that was published this year by the Hertie School of Governance. And Rosenow et al., the authors, they published analysis looking at how flexible heat pumps could help to avoid wind curtailment. And they found that heat pump flexibility in a system with a lot of wind generation significantly reduces the marginal electricity system costs of covering an additional megawatt hour of the heat pump's electricity consumption. So why is that? Why is there such a significant reduction of combining flexible heat pumps with wind? So the first reason they identified, and that's shown on this slide here, is that because heat pump load coincides relatively well with wind power generation, wind curtailment can be reduced. The second reduction potential for the cost of integrating heat pumps is around having system-friendly technologies. That's a term they use. And that essentially means having technology that's smart enough to schedule the heat pump in such a way that it avoids the hours where there's less wind on the system. And finally, thermal storage reduces that cost even further by adding further flexibility. And taken together, and I quote the paper here directly, the combination of wind power, system-friendly heat pump technology, and thermal storages can almost completely mitigate the heat pump cost increase. And they talk about the energy system cost increase here, which includes everything from generation, transmission, and distribution grids and balancing. So let's look at the third principle now. The third principle is to understand the emission effects and changes of load. And this is really important. It doesn't really matter so much anymore how much electricity we use, as much as it matters when we use electricity in a world that moves towards low carbon electricity. So as we add new electric loads, this is a really important consideration. And using averages for a kilowatt hour of electricity simply doesn't work anymore if we want to be honest about the emissions impacts of additional heating loads that are electric. So the carbon emissions per kilowatt hour consumed differ significantly over the course of a day. And this is what you can see on this graph. So there are 2 days here with data from Great Britain, from National Grid. And you can see the carbon intensity varies over the course of the 2 days by quite a bit. And what you want to do is to shift consumption to those hours when emissions are lowest to deliver the highest carbon emission reductions. And this also means that, again, if we operate electrified heating flexibly, that we can reduce emissions even further than the average figures that Richard shared with us earlier, which are simply based on the average grid factor. So there's already technology out there actually that runs heat pumps based on the emissions intensity of electricity. So this can be automated based on the information that is being fed to the smart control unit of heat pumps. And now the final principle that I would like to show you is to design tariffs to reward flexibility. As we demonstrated on the last slides, it makes a lot of difference when to use electricity, both in terms of carbon emissions, but also in terms of the energy system cost. And how do we actually encourage customers to shift their heating loads and participate in providing flexibility? Tariffs for electricity in Europe are mainly flat for most customers. There are some exceptions, but most customers are on a flat tariff. And there's no financial reward for shifting electricity consumption outside of the most expensive peak hours. So if you operate a heat pump, actually you see no benefit as a customer if you avoid the peak hours. There are also some emerging business models with some dynamic tariffs, and I'll show you one here. And this is an example from my own home in Oxford. And the blue line you see here presents the tariff which I'm on, which is called the Octopus Agile Tariff. And the price per unit of electricity actually varies every half an hour. Usually Octopus announces the tariffs for the next day, a day in advance. And you can feed that information to a smart device that controls the heat pump accordingly. The tariff varies significantly. You can see that in the peak hours, that's the secondary y-axis here, it shows the price per kilowatt hour. During the peak hours, it goes up to more than 20-25 pence per kilowatt hour, which is about 30 euro cents, depending on the exchange rate. So quite significant cost compared to the average cost in the UK for domestic customers of around 15 pence per kilowatt hour. And outside of those peak hours, prices can be very low and even negative sometimes. I'm sure some of you will have seen the news coverage recently I think that was about 2 or 3 weeks ago when electricity demand was really low because of the lockdown, and prices were negative for Octopus customers during certain hours when there was a lot of wind, a lot of solar on the system. And so by doing what I do currently, shifting consumption outside of those hours, and that's the red bars here, which show you the consumption, there are significant cost savings that can be realized. So about 95% of the electricity consumption of the entire house is off-peak, so outside of the hours 4 to 7, which is the peak period. And this is achieved by simply scheduling the heat pump in a way that automatically tracks the electricity tariff to minimize cost. And by doing that, I save about 50% of energy costs across the year, compared to having a flat tariff or a gas boiler, which is a significant saving, of course, and makes using a heat pump a lot more attractive, if we can reward customers in such a way. So those are the 4 principles I wanted to present to you today. I now have a few minutes left to talk very briefly about the policies needed to deliver on all of this. There are lots of different policies and regulations that will need to be reformed and implemented. And I will only briefly present to you the policy logic today. There's much more detail in the report about the different policy instruments that we feel will be needed to make all of this happen. So the policy logic consists of 4 essential steps, and they are on this slide. The first step is to reduce the energy demand for heating. And this can be done through energy efficiency policies, of which already we have quite a few, including building codes, financing schemes, energy efficiency obligations, and so on. And a lot of that is being facilitated in Europe through the Energy Efficiency Directive, Article 7. However, as Richard pointed out, this could be strengthened, and we currently don't achieve enough reduction in terms of energy consumption as well as carbon in the heating sector. The second step is that once we reduce demand, we will need to reduce the carbon intensity of the energy carrier further. And in case of heating electrification, this means reducing carbon emissions of electricity. And there's a whole range, of course, of existing policies already out there that are supporting that. And thirdly, we need to make sure that we phase out fossil fuel heating systems over time and promote the low carbon alternatives. And there's probably going to be a policy mix that's required, consisting of policy instruments, including regulations, but also financing instruments and energy efficiency obligations, similar to those encouraging reducing heat demand. And finally, electricity pricing will be needed to encourage flexibility. If we don't have the right price signals, it will be very difficult to actually incentivize customers to shift their heating loads, which will result ultimately in higher costs for the energy system that will be paid by everybody. So there's a good case to be made for offering more granular price signals. So I encourage you to look at the report for further detail on this. I have one more slide to conclude, and then I look forward to seeing your questions and comments. I look forward to that. So the conclusions from this presentation are that first, decarbonizing heat is critical for meeting the climate and clean air goals. And Richard has shown that with the data very clearly that without doing that, it's unlikely that we get anywhere close to the goals of the Paris Agreement, let alone net zero. The second conclusion is that electrification is a central pillar, certainly in the next 5 to 10 years, in our view, and possibly beyond that. Yes, there's some uncertainty, but it's unlikely that electrification will not play a big role. Quite how big the role will be, nobody knows, and we will find out as we roll out more of these technologies. And thirdly, energy efficiency is really critical to minimizing costs and to build in thermal storage. Without energy efficiency, it's going to be a lot more costly and a lot more difficult to do this. Flexible operation of heat pumps is possible, and there's actually evidence for this. We can talk about that later on, perhaps in the discussion, that this works. And this can be incentivized through having smarter tariffs and rewarding customers for that flexibility. And finally, we need a whole range of policy instruments to accelerate the replacement rates of fossil heating technologies. There's a lot of work for us, but we are optimistic that the opportunities have never been greater, and there's a lot of possibilities for making this happen. So thanks for listening. I look forward to the discussion, and I hand back over to Hans again for moderating the discussion. Thank you very much.